Okay, so thank you, Professor, for inviting me. So I'm not a specialist of biochar, but I work on a lot of things around biochar. And then I will present you a few things about combustion and gasification of biomass, biochar and RDF. Just a few points on the different things I will show you. So, like an introduction, I work on energy by thermochemical waste processes from biomass and waste. We have in my team a global approach. That means we work from the characterization of the fuels to the life cycle assessment of global processes. We don't make really the life cycle assessment for the moment, but we work with people where we done it, and so we give them all the data to make the life cycle, and we discuss together to do it. And the other specialty of our team is that we work mainly on experimental ways and with the big systems. I will show you one of them, but we have a lot of different systems which are at level 1. That means we work on semi-industrial plants, and all what we do can be transferred directly to industry, and we have a lot of work with industry. So I will present you a few ideas on combustion and gasification with biomass, RDF and biochars. I think you know all this, but thermochemical waste are different mainly by the oxygen content of the atmosphere. Sorry, the atmosphere of degradation. This I thank Anthony, because it's a job of Anthony, this one. But all people of Nancy use it now, it's well known. So I will only speak to you about combustion and gasification. Combustion is a total oxidation which lead to the exhaust of CO2 and water and little of ashes, and it's used to make heat or power or electricity, for example. And I will speak also of gasification, which is a partial oxidation with something like 30% of the oxygen content necessary to make combustion, and just to transform the fuel in gas, and after the gas can be used for different way, depending of the composition and depending of what we can use after. So we can make some cogeneration, some molecules and so on. Pyrolysis and liquefaction, we don't talk about now. In this diagram, we can show the difference between biomass and coal. The difference is that in the coal we have no oxygen or very low oxygen content, and the hydrogen content is also lower than in biomass. So the difference of biomass and charcoal is mainly the content of oxygen. There is not only this, but for only combustion, it's a big difference. And when we increase the temperature of treatment of biomass, you have seen here, we go from the biomass to the coal. If we look about some general data on biomass, biochar, and char, so it's global data, so we have a lot of difference possible, for example, for biomass. But we can see here the main differences are on carbon content. For biomass, it's something like 50%, yes, and it can be lower. For biochar, it's something like 70%, 75%, but it can be different depending on the severity of the treatment. And for char, it's a little higher, and we can reach more than 90%. And also a big difference is the volatile matter. In biomass, we have a lot of volatile matter. That means when we make the pyrolysis, we have a lot of gas and few fixed carbon. And with biochar, we have a big difference depending on the severity of treatment. If we have a low treatment, we have a lot of volatile matter. If we have high temperature treatment, we have lower volatile matter, and in the char it's also different. This is important because for the combustion, we don't burn exactly the same thing. When we burn some biomass, we burn mainly the gas issued from the pyrolysis of biomass. So we need a big chamber of combustion. If we burn char, we burn mainly the solid. So we need a big grid or a big system where we put some air, but we don't need a big combustion chamber because we have not a lot of gas to burn. So with different systems, it's difficult to use the same system for biomass and for char, but we can adapt a little. The two main technology here is for production of electricity. I speak only about this. So it's a big plant, and we have two main technologies. The first one is circulating fluidized bed. The second one is pulverized fuel systems. So the main difference between char and biomass, for example, is the size of the chamber. So, sorry, I don't use a good one. Here you see the chamber of combustion for char. If we use biomass, we need to increase the volume of this chamber and maybe also to change a little the position of the burner. And when we do this, we can change a plant from biomass to char or from char to biomass. And we need also to adapt the power because we have less energy in biomass than in char. So by modification of the volume and the power, we can change a little the utilization. This is well done in some countries. In France, we have one example in Gardanne of char plant, which will be transformed in biomass plant. The main problem is after the quantity of biomass necessary, which is very important, and it's not very interesting, I think, to make a lot of transportation to use biomass. So I think it's not a good idea, but it's possible to do it. The main goal now on these plants, when we use char and more and more when we use biomass now, is to reduce the CO2 emission. There is three main ways to do it. The first one is to do not change nothing. Quasi do not change nothing. That means we make the combustion, we make the treatment of gas for NOx and SOx, for example. And after this, we have some smokes, and we try to keep the CO2 in the smokes. So this is what we can name post-combustion CO2 capture. And after, the CO2 can be stored and used. Depends of what we can do. But the problem of this system is that the concentration of CO2 in the smokes is very low. It's something like 20% maximum. And because we have a lot of nitrogen due to the air injection at the entrance. So it's we need a big treatment just for 20% of the smokes, and so it's very expensive. Yes, it's very expensive for few CO2 concentration. Second system is oxy-fuel combustion. That means we use air. We separate air into nitrogen and oxygen. The nitrogen is put out, and the oxygen is used to burn the fuel. But if you use only oxygen, we will have a lot of problems of combustion control. Also high temperature, we have a lot of problems with materials and so on. So to be able to do it, we make a loop of the smokes. So here we take a part of the smokes, we coming back at the entrance, which is mixed with oxygen, and go back to the power generation. That means in the smokes at the exhaust, we have only CO2 and water, and a small part of oxygen. So if we condensate the water, in the smokes we have almost CO2, something like 90-95% of CO2. So it's easier to separate the CO2 and to store or use it. So it's a solution used now often in combustion of char, which is in development now for combustion also of biomass and other things. The last way, there is other, but the three mains are these. Last way is the pre-combustion CO2 capture. That means to try to keep the CO2 before the combustion. So here we use the gasification. So we gasify the fuel with oxygen and steam, which make a lot of hydrogen and CO2. Not only, but a lot of hydrogen and CO2. And we can use water gas shift system if we want to increase the hydrogen and CO2 production. And then we can separate the hydrogen and the CO2. The CO2 is stored and used, and the hydrogen can be used after as fuel in the power generation for different kind of systems. So it's another thing we can use. So these different systems are well known for coal combustion, but now are more and more used also for biomass and other fuels. You can see here an example. The smokes exhaust, the exhaust of smokes is here, and we recirculate a part of the smokes here to go here with air. Oxygen coming from here is mixed and is introduced in the system. Okay, so I will speak now quickly about gasification. So this is a sham photo of our plant I will show you later. So gasification starts like other thermochemical processes by pyrolysis. The pyrolysis gives some gas, some tar, and some char, and we burn a part of this to make heat to be able to continue the pyrolysis and the gasification, and also to produce CO2 and H2O. And CO2 and H2O, which are here, can react with carbon to make CO and hydrogen. So it's a little more complicated, but it's a resume of the gasification. So the main parameters we can be changed on this kind of system is the temperature, the equivalence ratio, the atmosphere. We can use air, steam, oxy-steam, and so on. We can change also the material of the bed. We mainly use olivine, but we can use other things. There is other parameters, but these four are the main. And the impact is on the gas quality and quantity, and the tar conversion, which is a big problem because tar is one of the main problems of gasification if you want to use the gas after. And also the char quality and quantity, I will go back from this. So this is our gasification plant. I will not detail all. It's a bubbling fluidized bed system. The reactor is a part 3 in the shell. After we have two collections of ashes, which are number 4 and 7. Number 4 is a cyclone system to take off the big particles, and the number 7 is a back filter system to keep the small particles. We have also in 5 tar cracking reactor to be able to reduce the tar content if necessary. We can use or not yet. And at the exhaust on 9 and 10 we have some scrubbers to take away the tars. So here we have a photo of this device. It's a semi-industrial one. The power is 250 kilowatts. We enter 50 kilograms per hour of fuel in the system. And when we make some tests, it's for 1 or 2 weeks, working 24 per week. We can make fluidization with air or with oxy-steam, and we are authorized to use biomass and waste in our system. It's now 10 years we use it. So I give you a few results, and you can show different kind of gas depending of here, just depending of the equivalence ratio and the nature of the fuel. Here we have 2 wood chips. The difference is just the moisture content, but what is important is that we are able to work with moisture content more than 29%, which is quite important for a gasification plant. And if we use at the bottom pellets with low moisture content, you can see that the quality of the gas changes. We have something like, for example, hydrogen 8% and for wood chips with high moisture content, and we can reach more than 10% with lower moisture. The same for CO and so on. Here I give you some results for different conditions, mixing of wood and air, mixing of wood and oxysteam. So we can see the main difference is with air we have a lot of nitrogen, it's a white column, and with oxysteam we have no more nitrogen, and we increase also the level of hydrogen and CO2. It is the same with RDF. We can also increase the level of hydrogen and CO2 when we use oxysteam. So depending on what we need to make with the gas, we can change the composition by the parameters. If you want to make only cogeneration, the gasification with air is good and sufficient, we do not need more. If we want to make methanation or fuel, we need to use oxysteam. Here, just to have some contact with biochar, we have done some mass balance of the results, and we can see we have very low biochar at the exhaust, and I write biochar, but really it's not biochar. It's a mix of carbon and ashes. But if we look at the end, in the cyclone, the ashes content is between 25 to 50%, and in the back filter, it's more than 50%. That means it's not biochar. We have a very low carbon content. We have tried also to see if there is some possibility to use it like activate carbon. It's very low. So we don't know how to use it. Maybe here it's interesting to burn the biochar to collect a little of energy, maybe to help to dry a little the fuel, for example. And to finish, I present you some gasification of biochar. We have made these experiments a few months ago. So we make some biochar with by pyrolysis of wood pellets during 4 minutes at 550 degrees in a bubbling fluid ice bed. It's not so easy because we need to inject the pellets and to stop the reaction 4 minutes after in the bubbling fluid ice bed. So we have made a specific thing to put out all the bed and to cool the bed quickly. And so we collect this kind of biochar you have seen in the photo, and after we make the gasification under steam of this biochar, and we can reach something like 65-68% of hydrogen. So it's a good way to produce hydrogen, but maybe it's not the best way, depending on what we can show about the efficiency of the global system. So to conclude, we can use biochar for combustion or co-combustion, but I'm not sure it's the main way if it's really biochar. I think it's better to use it at materials than at fuel. But if you have some poor biochars, such as I have in the power gasification, maybe combustion can be an idea. The capture of CO2 from biomass and biochar is also a solution developed now to give maybe a second life of biogenic carbon. That means we use it as energy, and after, if we capture the CO2, it's biogenic carbon, and we can use secondly, for example, in methane or in sustainable aviation fuel. So it's a second life of carbon, biogenic carbon. So if we make a good gasification of biomass, we do not produce biochar. I know that there is a lot of people saying that with gasification we can produce biochar. Normally, if we do a good gasification, there is no more biochar. It's very important because I think people will try to sell gasification to produce char are liars, and it's very important to say that to make biochar, it's pyrolysis, it's not gasification. So gasification is a good way also to transform biomass or RDF in energy. We have shown the quality of the gas. And to finish, starch gasification can be a good way to produce hydrogen, but we need to be able to test the global process before to continue in this. So, thank you.
So, thank you, and you finish your talk.
Long live India and France friendship.